Hi everyone, thank you for coming to this talk. My name is Xiaoning. In this talk, my colleague Wei and I will talk about Arktos and Mizar. In the previous talk, Deepak and Fu has shared lots of information about Mizar, including its architecture and how Mizar works. In this talk, we continue to discuss Mizar, but from a different perspective. Mizar is an independent network service. This means it can support different computing clusters, like Kubernetes or OpenStack Nova or other computing clusters. In this talk, we talk about Arktos, our own computing cluster, and how its network model looks like, and how we use Mizar to implement such a network model. This is our agenda. Our talk mainly includes 3 parts. In the first part, we will first give a background information about the project Arktos and Mizar, so you can know what Arktos is and its relationship to the project Mizar. We also give a brief introduction to the 3 major features in project Arktos. As you will see, Arktos is derived from Kubernetes. So starting from the second part, we will talk about Arktos network model. You will see how Arktos network model is different than the flat model in project Kubernetes, and also what kind of elements we have in Arktos network model. Arktos network model can be implemented by different network providers. In the third part, we will focus on how we use Mizar to implement Arktos network model, including its CRD-based control plane and XDP-based data plane. I will cover the first part, and then Wei will talk about the network model and the control plane in the second part. And I will continue to talk about data plane after Wei. Okay, let's get started with the first part, project introduction. The first question you might have is, what is Arktos? Arktos is one of the 2 major projects under Project Centaurus umbrella. Arktos is for the large-scale cloud compute orchestration, while Mizar is for cloud virtual networking. Arktos and Mizar, they sit side by side, work together to build a large-scale cloud infrastructure. If you are familiar with the project OpenStack, you can think of Arktos as the rule of project Nova in OpenStack, while Mizar as the rule of Neutron in OpenStack. This probably will help you understand the relationship between Arktos and Mizar. Why do we want to start Arktos? Arktos' vision is a large-scale open-source cloud infrastructure for next-generation workloads. When we talk about next-generation infrastructure or next-generation workloads, the way we think of it is, if we look at it from application perspective, these applications are not only VMs, they are also containers, functions, and lots of them will be AI-driven applications. And if we look at the infrastructure is not only about the cloud data centers, it's also about edge sites and 5G, etc. And combining these 2 different perspectives, Arktos wants to build a next-generation cloud infrastructure with built-in optimizations for these new workload types and leverage this new infrastructure better. Because these workloads are not only about VMs, lots of them will be containers. Project Arktos decided to start with Kubernetes. It's derived from Kubernetes codebase. Therefore, we can have the mature container support that's already available in Kubernetes. But on top of that, we made a lot of core fundamental design changes. We already implemented 3 major features here. One is the unified container VM orchestration, and cloud scalability, and multi-tenancy. We are also planning some other features like cloud and edge scheduling, cloud edge secure communication, and AI optimizations. But for today's talk, I will give introduction to these 3 implemented features in the next few slides. Before we jump into the details of these three major features, I want to first give a high-level overview of the relationship between Arktos and Mizar. This diagram shows how Arktos and Mizar work together in a cloud data center. You can see all the hosts in a cloud data center are managed by Arktos and Mizar at the same time. On each host, we have a computing agent, which reports to the Arktos control plane. And we also have a networking agent, reports to the Mizar control plane. These components work together to schedule workloads on different hosts and make sure these workloads can communicate with each other. What I want to say here is, while this is a recommended combination, both Arktos and Mizar are independent services. They can work with different computing clients and networking services. For example, Arktos, its network model is based on plugin style. For Mizar, we have a plugin called Network Controller for Mizar. It's running in Arktos and interacting with the Mizar control plane to finish the integration between Arktos and Mizar. If we want to use another network service, let's say OpenStack Neutron or AWS, we can also do that. We just replace this plugin, this controller. Arktos itself is neutral to different network providers. Vice versa, on networking part, Mizar itself is also an independent network service. It provides its public APIs, and it can work with different computing clusters, regardless it's Arktos or Kubernetes or other computing clusters. Both of them are independent cloud services. They can work together, but they can also work with other networking or computing services. This is the architecture of Arktos. As we mentioned earlier, Arktos is derived from Kubernetes. If you are familiar with Kubernetes, you will see some similar components here. For example, we have API server, we have data stores, and we have a scheduler, and we have different controllers. But the key design change we made here, first is for scalability. For example, for data stores, we support multiple etcd clusters. Because for very large cluster, you cannot save all the data into one etcd cluster. In this case, we support multiple etcd clusters, and they can work together. And also, for the API server, in Kubernetes design, one API server will hold all the caches. This will not work if the cache data is too large. So we implemented partition for API servers. And for Kubernetes controllers, in the original design, they are active and standby architecture. So anytime there is only one controller instance is working. And we implemented the active-active architecture. So all the controller instances are working at the same time to balance the workload and provide high availability. This is about scalability. And we also implemented built-in multi-tenancy. In Kubernetes, there is no multi-tenancy. They only provide some level of isolation using namespace mechanism, but it's not strong enough for a multi-tenancy cloud infrastructure. We implemented a strong multi-tenancy model, so each tenant won't be impacted by other tenants. In fact, they don't see each other at all. And the third part is we implemented the unified container and the VM orchestration. The original Kubernetes, they only support containers, but we extend the pod definition to VMs. So both VMs and containers, they can be scheduled and handled in a similar way. And you can just use one resource pool to support all these workloads. I will cover all these details in the next few slides. In addition to these three features, we are also working on some new features like cross-cloud and edge scheduling, and cloud and edge secure communication. This we will talk about in some other talk. In this next 3 slides, I'm going to cover these 3 major features with a little more details. The first feature I want to talk about is the native VM support. Arktos is derived from Kubernetes, but Kubernetes only supports containers. We know in reality there are lots of VM applications in addition to container applications. Of course, you can use 2 different systems to orchestrate these containers and applications. But having 2 different systems will lead to many problems. For example, you need to maintain and evolve 2 different systems, and this system have different resource pools. It's not easy for you to move some machines from one resource pool to another resource pool. That's why we started this feature, native VM support. We added VM support into Arktos. So with one system, we can support both container applications and VM applications. In Kubernetes, there are also some efforts to support VMs, like a Kubevert, but they are taking an add-on approach. That means they introduce a new object like called VM for VM applications. And on top of that new VM object, they have VM replica set, VM stateful set, etc. What we do here is we have a native VM support. That means we didn't introduce new objects. Instead, we extend the pod object to contain the VM applications. On the left side, I have a screenshot. You can see within a pod, we can have a VM or have containers. And the experience is very similar to customers. They can use one pod object to contain VMs or applications. The good about this approach is because we are extending this pod object, all the other components on top of pod can work the same way and work with the VM application as well. So we can have unified scheduling, unified controllers and agent. We don't need a separate scheduler or controllers for VMs. After we have this native VM support, the value for customer is first, they can run their legacy VM applications and their container application together on a single cluster. They don't need to separate a different cluster for different applications. And second, in the container world, there are lots of popular, very useful workload patterns like a replica set, stateful set, etc. Now they can apply these orchestration patterns into VM applications as well. It's not only used for container applications. Now it's kind of 1 + 1 greater than 2. And the value for cloud provider is, first, they can only have one single resource pool. By resource pool, I mean this machine pool. This machine pool is shared by both container applications and the VM applications. They don't need to allocate different small resource pools. The resource utilization is much better. And second, they can just maintain and operate one single software stack. They don't have to maintain and evolve two different stacks. That's a bigger advantage of this native VM support. The next feature I want to talk about is multi-tenancy. In Kubernetes, there is no multi-tenancy. Kubernetes provides namespace as a basic mechanism to isolate workloads, but it's not enough for a true multi-tenancy environment. For example, multiple tenants need to make sure there are no naming conflicts for namespaces, and there are also lots of non-namespace scoped objects which are shared by all the tenants. So in Arktos, we implemented a built-in strong multi-tenancy model. We introduced a new isolation concept called tenant space. All the API resources are put in different spaces. Each tenant has a space, and by default, a tenant cannot access other tenants' space. So first, they are strongly isolated, and second, because all the resource objects are confined to one space, They don't need to worry about these naming spaces or different access controls. They simply have their own copy of the original resource hierarchy. Here, we show an example how a tenant has its own space T1, and they can put any resources under this space. And in the backend storage, we also put this space into the storage key, so they are stored separately. But this changes the API format and resource path. So we introduced another feature called short path. Basically, customers can still use their old API and URL to access their resources. Inside API server, we have a module which will dynamically translate this short path to the internal full path. And we do this based on the access credential associated with this request. So we know which tenant space this request should go, even the customer didn't specify the tenant space. With this approach, we implemented a transparent, strongly isolated multi-tenancy model. Now, different tenants can share a physical cluster, but each of them feel like they are using this cluster exclusively. They are not impacted by other tenants, and they do not even aware of the existence of other tenants. The last feature I want to talk about is the scalability. Kubernetes only supports a few thousand hosts, but this is not enough for a large-scale cloud platform, especially the public cloud. In Arktos, we made a few core design changes, and our scalability goal is to support 300,000 hosts with a single control plane. In order to achieve this goal, we make sure all the components in the cluster can scale out. First, for the etcd data store, we support multiple etcd clusters, and we change the resource version generation mechanism to ensure these different clusters can work together, just like a virtual large cluster. And for the API server, because each API server holds a copy of the cached data, we introduce the partition into API server. So API server can have different groups, and they can scale out. They are not limited to the capacity of a single API server machine. For the controller and schedulers, we also introduced the workload partition. Based on the hash key of the workloads, they are distributed to different controller instances, and these controller instances are working in an active way, so they can balance the workloads and also are highly available. With these three major changes, we make sure all the components in the system can scale out. There are no single system bottleneck. I think this is pretty much what I have for the first part. To do a quick recap, I introduced what Arktos is, its relationship with Mizar, and the key features in Arktos. Next, I will hand over to Hongwei. Hongwei will introduce the new network model in Arktos and how we use Mizar to implement this network model.
Thanks, Xiaoning. Arktos is developed on top of Kubernetes. Kubernetes has a very simple network model, which is a flat one. Looking at this picture, all our pods connect to each other by their IP addresses. The IP address is assigned from a single shared IP pool, which was specified when the cluster was bootstrapped. The IP address assigned to each pod must be unique. They can't duplicate. This single IP range conflicts with Arktos multi-tenancy because each tenant doesn't want to deal with the potential IP conflicts with other tenants. They just don't care. Looking at this picture again, there is another issue. Any pod is able to connect to all other pods in the cluster. This is fully connected. And this is the default behavior, which might not be desired in some situation where security is required. In order to overcome this limitation, Kubernetes introduced network policy to provide some level of network security. However, the security provided by this means is not very secure. It is able to regulate good guys, but it fails to prevent the bad guy doing malicious things. Let me explain a little bit. First, abuse or even misuse of labels would break the planned security, which is brittle in nature anyway. Second, it does not prevent a packet sniffer put at some places where the traffic is passing by and extract out the sensitive data. This is not secured. Besides that, many implementations for network policy security are leveraging a Linux feature called net filter. It might sound good to have fine-grained network policy. However, in nature, in reality, it leads to massive number of IP table rules, which in turn lead to non-negligible performance hit and increased network latency, which is not so good. In this flat network model, Kubernetes only have single shared DNS. This DNS singleton is not desired by Arktos multi-tenancy because each tenant only wants to see the name records of that tenant and does not want to know any name records from any other tenant. Since Kubernetes flat network model cannot meet the requirements of Arktos multi-tenancy, it is necessary to introduce a brand new network model here, which is isolated one. The primary goal for this isolated model is to provide strong isolation across tenant spaces and across network boundaries inside same tenant spaces. The strong isolation means resources allocated in one scope are unrelated to resource allocated in another scope. Taking a picture here, the resources allocated in tenant A has nothing to do resource allocated in tenant B. Looking inside tenant A, there are two networks. Resources allocated in one network has nothing to do those inside another network. They are totally isolated. In one network, it is still possible to apply the network policy to provide one more layer of network security if you want to. The network policy-based security is supplementary to the network-based strong isolation. They can live together. So we have a brand new isolated network model. The cornerstone of this isolated network model is network. The network is introduced by Arktos, and it is a new custom-defined resource type. Below is an example of an object of that type. The network object defined in this way represents an isolation boundary of network resources. This list are some network resources that are network specific. For example, parts of one network cannot access to and cannot be accessed by parts from any other networks. In this way, it provides a very strong isolation with regards to the network resources. We have described the Arktos isolated model and its core concept of network objects. Then, how does Arktos implement such an isolated model? The answer is, actually, Arktos by itself cannot achieve this model alone. It needs to work together with so-called network solution provider to fulfill this goal. Looking at this picture, the API server, which is the central data store for Arktos system, keeps the critical data needed for running cluster, including paths, services, and network objects, of course. Besides other built-in controllers, Arktos puts 2 additional controllers specially purposed for multi-tenancy and network isolation. One is tenant controller, the other is network controller, respectively. Whenever a new tenant is created in the system, network controller kicks in to ensure that there will be a default network object created for that tenant. Whenever a new network object is created in the system, the network controller kicks in to take action to create essential network infrastructures such as DNS. Besides the built-in Arktos components, the external network provider should put some needed components running as part of Arktos master. These running components are collectively called network provider controller suite. Typically, they include various controllers for node, for network, for service, for paths and ingress, etc. So, the Arktos built-in components, such as API server and built-in controllers, with the joint force provided from network solution provider, implements such an isolated model altogether. We had to talk about Arktos and the external network provider in general. Talk about how they work together at a very high level. Now, let's look at specifically Arktos working with Mizar. Mizar is a recommended network solution provider of Arktos. It has been introduced in previous talk. First, let's take a look at the node provisioning process. A new node joins a cluster. Arktos registers the cluster in the API server. The Mizar node agent will be installed by the daemon set, which is already running on the workload. Meanwhile, Mizar node agent, node controller will detect the new node and notify the Mizar system, requesting the Mizar system to prepare the node. How the node preparation goes is totally Mizar network provider implementation detail. After the node has been prepared inside the Mizar system, and the node agent has been properly installed on workload, that node can be marked as ready, and the Arktos will schedule pod to run on that workload in the future. Next, we will take another high-level view to see what would happen if a new network, a new pod, new service is being created. Look at this picture here. We have a tenant A. We already have two existing networks. Both have services, both have resources specific to them. The first thing we want to do is create a network. When the network is created, the DNS has been already deployed and running with the IP address assigned from the network specific range. The next thing is we want to create a new pod in the network. The pod gets its IP address assigned from the IP specific range as well, and is able to connect to other IP of the same network. For example, this pod is able to connect to the DNS by the IP. The next thing we want to do is create a service. The service gets its IP as virtual IP assigned. And the Mizar network provider will finish the plumbing to map this virtual IP to the real IP of the pod as a backend IP. What if now we want to add one more pod to the same service? The new pod will get its IP assigned properly, and the Mizar network provider will pick up the event and updates the backend IP pool for that specific service. Then it will balance the node between these two pods instead of the previous only one. The point is, Arktos, working together with Mizar network provider, is able to present a strongly isolated network model. That concluded my simplified view of Arktos and the Mizar control plane. I will hand it over to Xiaoning.
Thank you, Hongwei. Hongwei just talked about Arktos network model and how we leverage Mizar to implement the Arktos network model. It's mostly about the control plane, about these CRD objects. In this last part, I will talk about things happening on the workloads, including what components do we have on a workload, and what happens when a pod is launched, and what happens when a pod communicates with other pods and communicates with the service. Let me first start with the components we have on our host. If we look at this diagram, this shows all the components we have on our host. First, we have user space and kernel space on the host. In user space, we have two agents, the Arktos agent and the Mizar agent. They each talk to their own control plane and listening for the instructions from the control plane. And we also have a CNI plugin for Mizar. This CNI plugin is invoked by the Arktos agent, but it will interact with the Mizar agent to finish all the wiring work when a pod is launched. First, when this host is initialized, this Mizar agent will attach the XDP program on the main network interface. This is to process any incoming packets. At that time, because we do not have any pods scheduled on the host yet, so we do not have any per pod network namespaces. So what happens when a pod is created? First, when a pod is created, the Mizar network controller, or the plugin in Arktos, It will watch the event of the pod creation. It noticed a new pod has arrived. That plugin will call the Mizar control plane to create a corresponding endpoint for that pod, basically assigning the IP. And the Mizar control plane will notify the Mizar agent on this host, telling him, hey, I have a new endpoint created on this host. You need to initialize the virtual network interface for this endpoint. What the agent will create is a VS pair and attach the XDP program, the transit agent, on one end of this VS pair. Initially, this VS pair is created in the host network namespace, because at that time, the pod hasn't arrived on this host yet. It doesn't know which network namespace will be assigned to that pod. After that, the Arktos agent will get the pod definition from the Arktos control plane. It will create the network namespace for that pod, and it will call the Mizar CNI plugin to initialize the virtual network interface for that network namespace. Here, what it happens is different depending on it's a VM pod or a container pod. If it's a container pod, the work is simple. The CNI plugin will move one end, the other end of the VS pair, into the container network namespace, and this end of the VS pair will act as the VNIC of this container. So any packets arrived on this end of the VS pair will go out on the other end and captured by our transit agent XDP program. What happens for the VM pod is a little different. The CNI plugin will also move the other end of the VS pair into the network namespace. But because Kumo now cannot use this end of the VS pair as a VNIC directly, we have to do a little more wiring work. We will have a switch here, and we create a tap device attached to this switch, and we use a file descriptor of this tap device as a parameter to the VM, the Kumo process, as a VNIC device. We are trying to optimize this part to gain better performance. But for both cases, when this wiring work is done, the CNI plugin will return to the network agent, to the Arktos agent, basically telling it that the virtual network device has been set up in this network namespace, and the agent can continue to set up other stuff and start the pod. This is what happens when a pod is launched on a host, and how these components work together to set up the virtual network device for this pod. Now let's see what happens when a pod tries to talk to another pod with Mizar's XDP networking. This diagram shows the components on two different hosts. And we can see we have two pods, pod 1 on host 1 and pod 2 on host 2. Each pod has its own virtual IP. What happens when pod 1 talks to pod 2 is, first, the user space pod application. It calls some socket API to write some buffer data. And this part of data will be encapsulated by the network stack in this pod's network namespace, because each network namespace has its own network stack. It will eventually become L2 packet and arrived at this end of the VS pair. Because it's a VS pair, the packet will go out on this side and then captured by the XDP program. This XDP program, the transit agent, will encapsulate this packet to an overlay packet. To be exact, in Mizar case, it will be a packet based on Geneva protocol. And this overlay packet will go out through the main interface and to one of the bouncers. On this host, on the source host, it maintains a list of the bouncers for each subnet. So based on the pod 2 IP subnet, it knows what bouncers it have. And then it will randomly choose one bouncer based on the hash value of this 5 tuple. Let's say in this case, it chooses the bouncer on 10.003. So the outgoing packet will have an out destination with 10.003. When this packet arrives the bouncer maintains a map. It knows which host has which endpoint. So it knows that the target endpoint, the endpoint of pod 2, is actually hosting on host 2. So it will modify the out destination to 10.10.2. Actually, I made a typo here. Here should be 10.00.2. So the packet goes here, and on this host, the main XDP program on this 0 will decapsulate this packet and change it to an inner packet again, and send to the corresponding with pair, and then go up all the way to the pod 2. This is how the communication happens with this Mizar XDP program. But one thing I need to emphasize here is after the first packet, the XDP program on the source host will receive a packet telling it that the endpoint 2 is actually hosting on the host 2. So it will have a cache item on here. Next time, when another packet arrives for this endpoint, it will send directly to the host 2. So it won't go through the bouncer every time. This will save the latency. The last part is about the pod to service connectivity. In Kubernetes or in Arktos, a service is like a load balancer. It provides a stable service IP to a dynamic backend pod pool. So you don't have to use this dynamic pod IP directly. You can use this stable service IP. What happens with Arktos and Mizar is similar to the pod-to-pod connectivity. Here, the pod application, they just send the packets to the service IP. So here, let's say the service IP is 192.1.2. So this service IP is still in the overlay packet. It's the inner destination. But what happens at the bouncer is the bouncer maintains a hash table. It knows what backend pod is included for this service IP. So when it sees such a service IP, it will dynamically change it to one of the backend pod IP. So you will see for this overlay packet, the bouncer changes both the out destination and also the inner destination. And then this packet will be sent to the backend host, and similarly, similar to what happened to pod-to-pod communication, it's decapsulated and sent to the target pod. The direct path also works here. After the first packet goes through this process, there is a cache item will be created on the source host. So the next time, the packet will be sent to this backend pod directly, instead of going through the bouncer again and again. This is the end of our talk. So we talked about what Arktos project is, its relationship with Mizar, and its key features. And we spent lots of time on Arktos network model. We talked about how it's different than the Kubernetes flat network model, and how we can leverage Mizar to implement such a network model, including the CRD-based control plane and XDP-based data plane. If you have any questions, feel free to bring up. We also include some links here It points to our project repo and the design docs, roadmap milestones. Feel free to check out. That's all. Thank you.